How can we keep our data safe in times of quantum computing? Paradoxically, the answer lies also in quantum mechanics. Hi, my name is Dorian Schiffer, and I'm presenting my master's thesis on high-dimensional temporal entanglement for quantum key distribution. In times of advancing quantum computers and ever more sophisticated cyber attacks, quantum key distribution, for short QKD, promises to keep our data safe based on the laws of quantum mechanics themselves. In the situations we are interested in, the communicating parties, usually dubbed Alice and Bob, share an entangled quantum resource, for instance photon pairs, upon which they perform measurements, and based on these measurements' result, they may extract a secure key, secure in the sense that any attempt of eavesdropping on the key is being detected. In particular, we are interested in situations where the photons travel to Alice and Bob over the atmosphere. For instance, think of a satellite that hosts an entangled photon source, sending photons down to two different ground stations, potentially located very far from each other, potentially even continents apart. We simulate this situation with a free space channel right over the roofs of Vienna. Using this telescope behind me, we send entangled photons to the other side of the city, 10 kilometers through turbulent atmosphere. Turns out that the atmospheric conditions along this channel are approximately the same as for a low Earth orbit satellite downlink. However, noise from ambient and solar photons, losses, and atmospheric turbulence makes the task of distributing keys over this channel very, very hard. To actually overcome these issues, we resort to high-dimensional entanglement. High-dimensional entanglement is more robust to noise. If you think of entangled qubits like a pair of quantum coins, whose results are more strongly correlated than classically permittable, you can picture high-dimensional entangled photons like a pair of quantum dice. These dice can have different amount of phases, for example 6 or 8 or 12, you name it. The cool thing about our experiment is that we may change the number of phases that we use without actually changing the physical experimental setup. That means for a given loss and noise situation, we can go and look for the optimal set of dice that gives us the highest key rate or the highest entanglement dimensionality that we can actually witness. We generate our high-dimensionally entangled photons using this down-conversion source that we designed, constructed, and then characterized. Turns out that this source has a very high brightness while being stable over a long period of time and having a low complexity architecture. We then checked whether our photons are actually high-dimensionally entangled by running them through this local setup. Using the same experimental configuration, we could also test our QKD protocol under different loss and noise scenarios in-house. We didn't just show that the source actually works, we also demonstrated an advantage in key rates in dimension 4 over dimension 2, demonstrating for the first time that higher dimensions can yield higher key rates, albeit for a lossy and local situation only. This means that my thesis is an important step towards realizing the QKD experiment over the free space channel, but also more generally speaking, a step towards realizing quantum key distribution over long in-air distances. That's it from my side. Thank you for considering me for the ÖPG Student Award, and goodbye.